Howdy. We're going to talk about springs today. So you can see there's a couple of springs here. Springs can both be compressed. So I can compress this spring, it gets shorter. I'm applying force to the spring. And they can also be stretched. The cool thing about springs is that the more they're stretched, in this case, the more a spring is stretched, the more it resists stretching. And the same thing with compressing is true. The more the spring is compressed, the more it resists compression. And I can prove that with another example. So hopefully you can see this. What I have here is it's called a spring scale. And you might be able to tell on this, but there are some markings on this scale that are measured in newtons. And this measures force. And it can measure force because there's a spring inside that gets stretched. So as I said before, the spring, the farther it is stretched, the more it resists the stretching. And I can prove that because if I hang a 500 gram mass on the end of this spring, for instance, it stretches a certain amount. Right now it's reading 5 newtons, approximately 5 newtons. Okay? So what's interesting, according to Newton's third law, which we already know, is that the force of the gravity pulling down on this mass, because the mass is not accelerating right now, it must be equal to the tension force on the spring that's pulling up. And as I said before, the more I pull on the spring, the more the string resists pulling. For that reason, in order to pull the spring down more than this, in order to stretch it more, I have to apply a greater force. So for instance, I can double the mass, and the spring stretches even more. Now the spring is reading approximately 10 newtons. Now, I don't think this is blowing anybody's mind, because it's pretty simple that if you pull on a spring harder, it's going to stretch more. And actually there's an equally simple equation that applies to the math that's going on here, and that's called Hooke's law. That's what we're going to talk about today. So Hooke's law is the mathematical equation that governs springs. Basically, when you think about Hooke's law, you need to be thinking about springs. This can also apply to other situations that have to do with other kind of elastic things, like you can think about rubber bands or balloons or things that stretch or compress. Hooke's laws can generally describe those situations as well. Hooke's law, you might recognize the name Hooke. There was a guy whose name was Robert Hooke, who lived during the 17th century. And he's the one that came up with Hooke's law. He's the one that we attribute this law to. He's also the same guy that worked with biology. He looked at cork cells, and he was the one that kind of coined the term cell. He sort of invented the microscope. But we attribute Hooke's law in physics to Robert Hooke as well. And I've talked about this when I talked about Isaac Newton, and the same is true for Robert Hooke. A lot of the guys back then tended to be what we call Renaissance men, which means they were sort of jacks of all trades. And obviously we can say the same thing about Robert Hooke. He dabbled in some biology. He did some other things as well. And then obviously he's worked on some of the things we're going to talk about in physics class. And so he can sort of be what we call a jack of all trades. But Hooke's law. Hooke's law states that the restoring force of a spring is proportional to the displacement of the string. That's obvious. That means the more the spring is stretched, the greater the force the spring is going to exert to try to bring itself back to normal. Sometimes we call that the restorative force or restorative force. Restorative force. And the restorative force or the restoring force is equal to Kx. F equals Kx is our equation for Hooke's law, where again, F is the restoring force, and that force, since it's a force, is in newtons. K is the spring constant. The units for the spring constant are newtons per meter. Basically, all this means is the newtons of force that the spring applies per meter of stretch. Okay, and as I've already said, the more the spring stretches, the more force it's going to apply to try to bring itself back to its original shape. And all you really need to know with the spring constant is that the larger it is, the stronger the spring is. So the bigger the spring constant, the stronger the spring is. X is the displacement of the spring from its normal resting position. First of all, you need to know that X needs to be in meters, and that's very important because a lot of the displacement values we'll have with springs will be in centimeters, and so we're going to have to convert to meters. A couple of things you need to know about this equation. The first thing is that in this class alone, and it's different when you get to other classes and other segments of physics, this is just the basic Hooke's law. So for this class, what I'm really concerned about with this equation is magnitude only. I'm only concerned about magnitude here. In other words, we're not going to look at direction. I'm just looking at the magnitude of the force that is exerted by the spring. For that reason, this value of X, the displacement of the spring, needs to always be positive. Okay? And sometimes that means we might need to take the absolute value of what we're talking about. In other words, I just want to know how far the spring stretches, and that's our value for X. All right? Hooke's law in this class is very simple. It's going to be manifested in problems that sound like this. You have a jack-in-the-box. Everybody knows what a jack-in-the-box is. It says it's built around a spring with a spring constant of 70 newtons per meter. I'm going to circle that. It's a good habit to get into. Tell myself that that's K. That is the spring constant. How hard does the spring push? Well, they're asking for the force there. They're asking for the restorative force. How hard does the spring push when it compresses from 40 centimeters long down to 15 centimeters long? What they're giving you here is a method to find the displacement of the spring, the X. So if we go back to our good old guess method, let's see what we're given. They give us the spring constant, which is 70 newtons per meter. They give us the displacement of the spring, sort of. All we have to do to find that is it tells us that the spring is 40 centimeters long to begin with, and it gets compressed to 15 centimeters long. All I want to do is find the displacement. To do that, I just have to find the difference in the two numbers. 40 centimeters minus 15 centimeters. That gives me a displacement of 25 centimeters. But remember, when we calculate displacement, it has to be in meters. So I'm going to convert this. To convert from centimeters to meters, you have to move the decimal 2 places to the left. So the displacement here is 0.25 meters. That's our X. The unknown we're looking for here is the force of the spring. So you can put Fs or Fr for restorative force, or you just leave it as an F. It doesn't matter. You're trying to find the force, and we're going to use this equation to do it. So just so we can get an idea of what's going on, it should be fairly straightforward, but here's this spring in the jack-in-the-box that's originally 40 centimeters long, and we're going to compress the spring by closing the lid, and the spring is more tight in here until it's now 15 centimeters long. Okay, we found this X, we found that distance, the displacement rather, and that was 25 centimeters. I'm not concerned about the direction of this displacement for now in this class. I just want the absolute value, and it's 25 centimeters or 0.25. So our equation, we know quite obviously, is the one we've had up here, F equals Kx. K we know is 70 newtons per meter. X we found to be 0.25, and if we multiply those two, 70 times 0.25, very simply, you get 17.5 newtons. And Hooke's law is that easy. Hooke's law is not that big of a deal. There's, in this class at least, for on-level physics, and what we're going to do in here with Hooke's law is very simple. You don't need to know just a whole lot about Hooke's law. Let's do one more problem for Hooke's law. Let's do this one here. Says Tyler is hanging springs or using springs to hang art projects. He hangs a 3 kilogram picture on one particular spring and it stretches from 30 centimeters to 45 centimeters long. What is the spring constant? So they're asking us for K here. What's the spring constant for that spring? Well, let's go back up and look. 3 kilogram picture, that's a mass, okay? And we'll have to think about what to do with masses in just a minute, and I'll explain why. Right here, 30 centimeters to 45 centimeters long, they're giving us the positions, which is going to allow us to calculate X, or the displacement. All right. Let's draw this spring at its maximum stretch position. He has this picture hanging on there, and the mass of the picture is 3 kilograms. It's a really good idea. Sometimes they don't always work in these problems, but it's a good idea to draw a sort of free body diagram like this. The length of the spring at this point is 45 centimeters. That's the maximum stretch position. And what we can assume, and maybe we should come back up here to the X. When this says displacement of the spring, we need to add that this is displacement when the spring is at rest. Displacement when the spring is at rest, not when it's moving. Okay, so this is not the displacement of, for instance, let's say a bungee cord. When you jump and you're bungee jumping, the cord has a maximum displacement, right? So you may jump, if this is a bungee cord, here's a tower, and you jump off like this, the displacement of the cord may be something like this, and then you come back up. But if you bounce up and down a few times, you will eventually come to rest, and you're not going to come to rest down here. This is the maximum displacement. The X we're talking about for this equation is the displacement of the bungee cord, maybe somewhere in here, when you're just sitting there at rest. When you finally come to rest after bouncing up and down, what is this length of that spring or the bungee cord when it is at rest? So that's what we're talking about here. So if it says that the spring stretches from 30 to 45, I can assume that when the spring is 45 centimeters long, this picture is at rest. And when the picture is at rest, the free body diagram that we need to draw says that there's 2 forces going on. I know that there's a force of gravity. That's the weight of the picture that's pulling down on the spring. And if the picture's not moving, I know the acceleration is 0. And if the acceleration is 0, that means the net force is 0. So there must be another force pulling up on the object to keep it from accelerating. And that force, obviously, is, I'm going to call that the tension force in the spring, or the spring force, or the restorative force, whatever you want to call it. There's a force applied by the spring that has to be equal to the gravitational force. So I might go ahead and tell myself that the weight is equal to the tension in the spring. Givens. They tell me the mass of the picture is 3 kilograms. I can find the displacement by subtracting these two numbers. 45 minus 30 gives me 15 centimeters. Remember, we have to convert that to meters. That's going to be a very common thing we have to do. Centimeters to meters is 2 to the left. So you get 0.15 meters. And that's pretty much all they give us. The unknown, what they want us to find, is K, the spring constant. It says right here. Okay? The equation we're going to need. Obviously, we're going to use F equals Kx. That's the same equation we've been using for springs, for Hooke's law. But the thing about this is, to find K, we have to know the force, and we have to know the displacement. We know the displacement. We found that. But we don't know the force yet, which is where we have to come back over here and reason that the gravitational force must be equal to the restorative or the tension force in the spring, which is really the force that we're trying to find. So we need to find the gravitational force, because once we find that, because the picture's not accelerating, we've also found the restorative force of the spring. So let's come over here and remember that to find the weight or the gravitational force, that's just simply the mass times the acceleration due to gravity. Mass of the picture is 3 kilograms, which is why we need that. Acceleration due to gravity, negative 9.8. And we find that the weight is equal to 3 times negative 9.8, which is negative 29.4 newtons. All right? And so the tension force is going to be the positive of that, because the tension force goes up. So the tension force, 29.4 newtons. So now we have everything that we need to know. This force can come over here and plug in for the force in our equation. 29.4 equals K times 0.15. And divide both sides by 0.15. And you will find that the spring constant is 196 newtons per meter. There you have it, Hooke's law.